Alright, so what we're going to try and do is we're going to try and set up how our two source interference problem, so here I've got two sources, like what we were talking about in class at the end of last week, how those are going to lead to the interference pattern that we're going to see on the screen. So for starters, here are my two sources. Here's the line that separates them. And then what's going to happen is they'll each start sending out signals. And so you'll see that basically they'll start sending signals outward. And this, if we sort of stop it at some point in time, this is what we'll have, some chunk of time later. And so what we want to do is we want to understand what this pattern is trying to tell us. So for starters, let's be clear about what the red and blue means. So basically what we're saying is, we happen to have stopped when we're just about to emit a source from each source, or the wave we're emitting from each source is just about to emit another peak. And so here's a peak, and then it goes half a wavelength to a trough, then back to a peak. So sort of going from red to blue to red, that's one full wavelength. And then here's another, so here's where you're going to see the next trough, then the next peak, the next trough, the next peak. So when you're thinking about our sine curve, right, all the red is trying to do is be a point of maximum amplitude positive, and the blue is just a point of maximum amplitude negative. And so what we're going to be interested in is how the peaks and troughs add up. So the first thing that we'll notice is if you look at the line running right down the center of the pattern. So one of the things that we talked about in class on Friday is that this line running down the center, any point on this line, you know that the wave from our source on the left has traveled exactly the same distance as the wave from the source on the right, and so that's why you see troughs lining up with troughs, peaks lining up with peaks, troughs and troughs, peaks and peaks. So what this means is this line down the middle of our pattern, it happens to be the minimum path difference that we ever have, because here's where the path difference is 0. And so this is going to be this will always be, this center point in our pattern will always be a point of constructive interference. So we're going to have the minimum path difference. So this is going to be where the path difference equals 0, which means this will be a maximum within our pattern. Okay? Now the other point of interest is basically thinking about, so what happens if you sort of, again, we talked in one of the problems on Friday, so if you start along this center line and start walking in some direction, and as you get infinitely far away, that's basically like saying you're on this line here. And so the other thing that's interesting is thinking about what's going on the line that connects our two sources. And if this center line is the minimum path difference, one of the things that's sort of obvious when you think about it is that the line that connects our two sources, that line is actually going to be the maximum path difference. So however far the sources are separated, continuing any point on this line, so here we happen to have, so there's one wavelength, there's two wavelengths of separation between our sources, which means that 2 wavelengths is the maximum path difference you'll ever get. So if you were thinking off in some direction up here, well, that's going to be greater than a path difference that's greater than 0 and a path difference that's smaller than 2 wavelengths in this particular case. So these are sort of the 2 starting points. This is going to tell us we know that there's going to be a constructive interference line in the center, because that's going to be where the path difference is 0. And we know that what's going on along this line is going to tell us, in some sense, what's the largest path difference we'll ever get. So when looking at this pattern, what you notice is we've said the maximum path difference that we get happens to be 2 wavelengths, because that's how far these sources are separated. So if you sort of look for these other lines, you see here happens to be a line where, so if I come from here, So here's a point where trough and peak, trough and peak, trough and peak, trough and peak. So this is actually a line where everything is canceling out. This is the line that corresponds to half a wavelength. I keep coming over and now I see troughs and troughs, peaks and peaks. So here's where everything's lining up, another constructive interference. This is going to be one wavelength for the path difference. I've got another destructive interference line where peaks and troughs are overlapping. And then that's it. The last thing I get happens to be this line where the path difference is 2 lambda. So knowing what this distance of separation is basically tells me how many maxima and minima I can possibly have in my pattern. Because if I know that I've only got 2 lambda worth of separation between my sources, then the only options I'm going to have in my pattern are 0 lambda, a maximum, half lambda minimum, 1 lambda maximum, 1.5 lambda minimum, and then a 2 lambda maximum. So that's kind of what we're looking at here. So again, if we look on the next screen, so the image is a little bit blurry, but I think hopefully we're seeing the same thing here. So again, what you're seeing from your 2 sources is you're seeing these lines that correspond to places where both waves add up, right? Constructive interference, both waves cancel out, destructive interference. And how much separation there is between your sources is going to dictate sort of how many of these lines you can possibly have. So in this case, we know that we're going to have a path difference of 0 because we always have that one present. We know we're going to have a path difference of 1/2 wavelength in this case. We see that we've got a path difference of 1 wavelength in this case. Here's the line for a path difference of 1.5 wavelengths. So here's a line for 2 wavelengths. And so again, we've got a situation where if I think about placing a screen out here, then what I'm going to see on the screen is basically going to be a bright spot, a dark spot, a bright spot, a dark spot, a bright spot corresponding to these places of constructive and destructive interference. So you'll see that when we take, and again, you see this pattern on both sides. So whatever's happening over here, the same thing's happening on the other side of the pattern. And so when you look at a screen, what you get are a series of bright and dark fringes. So here's the central bright maximum. This is where the path difference is 0. And then you're going to have all this intermediate interference until you get right here. And this is the first dark fringe. And this dark fringe is going to correspond to where the path difference is 1/2 wavelength. Then you'll have intermediate interference that builds back up until you get to constructive interference of 1 wavelength. Intermediate interference until they now cancel out. Intermediate interference until you get a bright fringe again. So we'll talk about the central bright maximum. And then the bright fringes are these extra things off to the side, and the dark fringes are also off to the side. So basically what we're going to do is, again, if you look at this pattern and you say, well, what we see 0 wavelength, 1/2 a wavelength, 1 wavelength, 1.5 wavelengths, 2 wavelengths, 2.5 wavelengths. We never really get back to that line of 3 wavelengths. So this tells us that our 2 sources are separated by something just under 3 wavelengths. Right? And so the pattern we expect to see should represent roughly that. So you're seeing the 0, 1/2, 1 wavelength, 1.5, 2, 2.5. So this is sort of showing the last bright fringe right here at the edge of the pattern, which means that your sources are basically separated right at about 3 wavelengths. So what we want to do, so the whole idea of this is, when we start looking at interference patterns with light, this is the way the pattern is going to look. And so we want to understand how this behavior of waves gives us this pattern. That's the idea.